All right, so get this. What if we could bottle the power of the sun? I don't mean solar panels. I mean the actual nuclear fusion happening at its core.
Yeah.
It sounds pretty sci-fi, right? But that's exactly what researchers are trying to do, and we're diving deep into some news that has everybody buzzing.
What's fascinating here is that this isn't just theoretical anymore. We've got concrete evidence that we're moving in the right direction thanks to a major breakthrough in China.
Okay, so you're talking about the experimental advanced superconducting tokamak, or EAST, which just held superheated plasma for over 17 minutes. That's longer than any other fusion reactor has ever managed. But for those of us who don't have a PhD in nuclear physics, what does that actually mean?
It means we're getting closer to a future powered by clean and limitless energy. East, sometimes called the artificial sun, uses powerful magnetic fields to contain plasma 7 times hotter than the sun's core. The goal is to fuse atomic nuclei, just like what happens in stars, and release enormous amounts of energy.
So it's basically like creating a mini star right here on Earth. That's mind-blowing. But why is this 17-minute achievement such a big deal?
Think of it this way. Previous reactors could only hold plasma for a few seconds at these temperatures. 17 minutes is a huge leap. It demonstrates a level of control and stability that we haven't seen before. We're finally mastering the delicate balancing act needed to sustain a fusion reaction for a significant amount of time.
That makes sense. So how do they actually create and control this superheated plasma? I mean, we're talking about temperatures hotter than the sun.
Well, it starts with a donut-shaped device called a tokamak. East uses superconducting magnets to generate a powerful magnetic field. It essentially creates a magnetic bottle to contain the plasma, but getting it to those scorching temperatures, that's where things get really interesting.
All right, I'm all ears. Break it down for me.
Um, Imagine hitting something with a hammer over and over. That's kind of what they do, but with energy. East uses a combination of radio frequency heating, which beams radio waves into the plasma, and neutral beam injection, which fires high-energy neutral atoms into the mix. It's like bombarding the plasma with energy from all sides to get it superheated.
Okay, I think I'm starting to get it.
Ah.
But with all that energy being pumped in, how do they keep the plasma from touching the reactor walls and causing a meltdown?
That's where sophisticated control systems come into play. They constantly monitor the plasma's density, temperature, and position, making minute adjustments to keep it perfectly balanced within the magnetic field. It's like a high-wire act, but instead of a person, they're controlling something hotter than the sun.
That's insane. But it sounds like they're not just heating the plasma, they're also trying to optimize how well it holds that energy,
Yeah,
right?
exactly. And that's where a key concept called high confinement mode, or H mode, comes in. Imagine a whirlwind. That's what turbulence does to the plasma, making it lose energy. H mode is like finding the eye of that storm, a calm center where we can trap the heat more effectively.
So it's not just about reaching high temperatures, it's also about making the plasma act in a way that keeps it stable and energy efficient.
Precisely. And East achieving this H mode for 17 minutes is a major step toward what we call ignition, the point where the fusion reaction becomes self-sustaining. Think of it like a campfire. You need kindling and constant attention at first, but once it gets going, it burns on its own.
That's an amazing analogy. So 17 minutes may not sound like much compared to the lifetime of a star, but in the world of fusion research, it's a game changer. But East isn't the only player in this game, is it?
Absolutely not. East's success is just one piece of a much larger global effort to achieve fusion power. There's the International Thermonuclear Experimental Reactor, or ITER, a massive international collaboration being built in France. But East is a crucial testing ground, a proving ground for many of the concepts that ITER and other future reactors will rely on.
So it's like the minor leagues, but for fusion power.
In a way, yes. East allows researchers to experiment with different approaches, test new materials, and push the boundaries of what's possible. And the lessons learned from East will directly inform the design and operation of larger, more powerful reactors in the future.
It's incredible to think about all the brilliant minds working together on this.
It really is. There's a real spirit of collaboration in the fusion community. Everyone recognizes the immense potential of this technology to solve some of humanity's biggest challenges, and they're sharing knowledge and resources to make it happen. It's inspiring to see.
But as with anything groundbreaking, I imagine there are still challenges ahead.
Oh, absolutely. While East's achievement is a huge leap forward, we're still a long way from plugging our homes into fusion power plants. There are significant hurdles to overcome, and that's what we'll delve into next.
All right, I'm ready for the next level of this deep dive.
We were just talking about some of those challenges on the road to fusion power, right? And one of the biggest is actually a material science problem.
Oh, That's interesting. I guess I always assumed it was all about the physics of the plasma itself. But it makes sense. You're dealing with something hotter than the sun. What kind of materials can even handle that?
It's mind-boggling, isn't it? We're talking about temperatures that would vaporize most things in an instant. That's why researchers are constantly searching for and testing new materials that can withstand the extreme conditions inside a fusion reactor.
So what kind of materials are we talking about? What's the magic ingredient?
Well, there's no single magic bullet. But one material that's shown a lot of promise is tungsten. It has the highest melting point of any element, which makes it a prime candidate for lining the inner walls of the reactor where it comes into direct contact with that scorching plasma.
So it's like a super shield protecting the reactor itself from being vaporized.
Exactly. But it's not just about the heat. The materials also need to resist erosion from the constant bombardment of energetic particles coming from the plasma.
I can imagine that would be a huge issue. Over time, even the toughest material would start to break down, right?
Absolutely. And if those eroded particles get into the plasma, they can contaminate it and disrupt the whole fusion process. So finding materials that can withstand not just the heat, but also the constant wear and tear is a crucial part of making fusion power a reality.
That's fascinating. So it's not just about finding a material that can take the heat. It also has to be durable enough to last.
Exactly. And on top of all that, these materials also need to be compatible with the magnetic fields used to contain the plasma. Some materials can actually interfere with those fields, which can throw the whole system out of whack.
Wow, so there are all these interconnected factors to consider. It's like a giant high-stakes puzzle where every piece has to fit perfectly.
That's a great way to put it. And it's not just the materials themselves, it's also about how they're manufactured and assembled. You need to ensure there are no imperfections or weaknesses that could compromise the integrity of the reactor.
So even a tiny flaw could potentially lead to a major problem.
Precisely. That's why the engineering and manufacturing processes are just as important as the materials themselves. It's a testament to human ingenuity that we've been able to make so much progress in developing materials that can handle these extreme environments.
It really is incredible. But materials are just one piece of the puzzle, right? We also need to talk about how they actually monitor and control the plasma itself.
Absolutely. That's where diagnostics come into play. EAST, like any advanced fusion reactor, is equipped with a whole suite of sophisticated tools to monitor the plasma in real time.
So they're basically keeping a constant eye on this superheated cloud of energy.
Exactly. They're measuring things like the plasma's temperature, density, and composition. They're also tracking how the plasma is moving and behaving within the magnetic field.
It sounds like trying to track a swarm of bees, except the bees are hotter than the sun.
That's a pretty accurate analogy. And just like with a beehive, you need to understand the patterns and behaviors to keep everything running smoothly.
So what kind of tools are they using to do this? What does a plasma thermometer even look like?
Well, they use a variety of techniques, each designed to measure a specific aspect of the plasma. For example, they use something called electron cyclotron emission detectors, which measure the temperature of the electrons in the plasma by analyzing the electromagnetic radiation they emit.
Okay, so it's not like a physical thermometer you'd stick into the plasma. It's more about analyzing the energy it's giving off.
Exactly. They also use things like reflectometry, which uses microwaves to measure the density of the plasma, and spectroscopy, which analyzes the light emitted by the plasma to determine its composition.
So they're essentially using different wavelengths of light to probe the plasma and gather information about what's happening inside.
That's a great way to put it. And all of this data is fed back into the control systems, which make tiny adjustments to the magnetic fields, heating systems, and other parameters to keep the plasma stable and within its desired operating range.
It's like a constant feedback loop where they're making tiny adjustments to keep everything balanced.
Precisely. And the more data they can collect, the better they can understand and control the plasma. It's all about refining the process and pushing the limits of what's possible.
It sounds incredibly complex, but also really exciting. You're essentially trying to tame one of the most powerful forces in the universe.
It is incredibly challenging, but also incredibly rewarding. And remember, we're just scratching the surface of what's possible. Every experiment, every new piece of data brings us closer to making fusion power a practical reality.
And speaking of challenges, we talked earlier about turbulence being a major hurdle. How are they tackling that problem?
That's a great question. And it's one of the most active areas of research in fusion science. Turbulence, as we mentioned before, is like this chaotic swirling of the plasma, and it can lead to a significant loss of energy.
Right, it's like trying to heat a house with all the windows open.
Exactly. So researchers are exploring various methods to tame turbulence and improve the confinement of the plasma. One promising approach is to use magnetic fields to shape and control the plasma flow, creating what's known as a transport barrier.
So it's like building a magnetic fence to keep the energy from escaping.
Yes. And EAST has demonstrated remarkable progress in achieving these high confinement modes, where turbulence is significantly reduced. But it's still a very complex problem, and there's a lot more research to be done before we fully understand and can control turbulence.
It sounds like there's a lot of trial and error involved, constantly pushing the boundaries and learning from each experiment.
Absolutely. Fusion research is a journey of discovery, and every step forward brings us closer to a future where clean, abundant energy is a reality.
It's inspiring to see the dedication and ingenuity of the researchers working on this. They're not just solving scientific puzzles, they're working to change the world.
I couldn't agree more. And it's not just about the science, it's about international collaboration, sharing knowledge, and working towards a common goal that could benefit all of humanity.
Well said. But we have to acknowledge the elephant in the room. Even with all this progress, fusion power still seems like a distant dream for most people. What are the biggest challenges standing in the way of making it a reality?
That's a question we'll dive into next.
So we've been talking about all these incredible advancements in fusion research, specifically the record-breaking achievement of China's East reactor.
It's truly a remarkable feat holding superheated plasma for over 17 minutes. But, as we've discussed, there are still some significant challenges on the road to commercial fusion power. What are some of the biggest hurdles we need to overcome to make this dream a reality?
One of the most daunting challenges is scaling up. East is an experimental reactor designed to test concepts and push the boundaries of what's possible.
Right, it's like a proof of concept. But to actually power cities, we'd need reactors many times larger.
Exactly, and building those larger reactors presents a whole new set of engineering challenges. The materials, the magnets, the control systems, everything needs to be scaled up proportionally, and that's no easy feat.
So it's not just a matter of making everything bigger, it's about ensuring that all the components work together seamlessly at that larger scale.
Precisely. And there are also logistical challenges, like finding suitable locations to build these massive reactors and ensuring the safety and security of such powerful facilities.
It's a massive undertaking, for sure. But let's assume we can overcome the engineering hurdles. What about the fuel? We talked earlier about how tritium, one of the isotopes of hydrogen used in fusion, is relatively scarce.
That's another major challenge. We need to find a way to produce enough tritium within the reactor itself to keep it running sustainably, right? Otherwise, we'd be relying on external sources, which are limited and expensive.
So it's like trying to build a car that can generate its own gasoline as it drives.
That's a great analogy. And that's where the concept of tritium breeding blankets comes in. These blankets would surround the reactor core and contain lithium.
And lithium, when bombarded with neutrons from the fusion reaction, produces tritium.
Exactly. So in theory, you could create a closed-loop system where the reactor is constantly replenishing its own fuel supply.
That sounds incredibly efficient, but I imagine there are technical challenges involved in making that work in practice.
There are. Designing and engineering these breeding blankets is an active area of research. We need to ensure that they can withstand the harsh conditions inside the reactor, that they produce tritium efficiently, and that they don't introduce any impurities into the plasma.
It's like adding another layer of complexity to an already incredibly complex system.
It is, but it's a necessary complexity if we want to make fusion power a truly sustainable energy source. Okay, so you've got the engineering challenges of scaling up and the fuel challenges of tritium breeding. What other hurdles are standing in the way?
Let's not forget about cost. Fusion power needs to be economically competitive with other forms of energy if it's going to be widely adopted.
That means bringing down the cost of building and operating these reactors.
And increasing their efficiency. The more energy we can get out of the fusion process, the more cost-effective it becomes.
So it's a delicate balancing act between pushing the boundaries of what's scientifically possible and ensuring that the technology is commercially viable.
Precisely. And that requires collaboration between scientists, engineers, policymakers, and industry leaders.
It's a truly global effort, and it's inspiring to see so many people working together towards this common goal.
It is, and let's not forget about the public perception aspect. Some people still associate fusion with nuclear weapons, but it's important to emphasize that fusion is a completely different process.
Absolutely. Fusion is inherently safe. There's no risk of a meltdown like with traditional nuclear fission reactors, And the waste products are far less radioactive and much easier to manage.
So it's about educating the public and dispelling those myths.
Right. Fusion has the potential to provide clean, safe, and abundant energy for the world, but we need to make sure that people understand the facts and the benefits.
It's about building trust and excitement for this transformative technology.
Well said.
Yeah.
So with all these challenges in mind, where do we go from here? What does the future hold for fusion power?
The future is bright, but it's also uncertain. We've made remarkable progress in recent years, and East's achievement is a testament to that, but there's still a long way to go.
But the global fusion community is more determined than ever to overcome these challenges. We're seeing increased investment, new collaborations, and innovative approaches.
So it's a time of both excitement and anticipation. It's a time to push the boundaries of science and engineering, to dream big, and to work together towards a future where fusion power becomes a reality.
A future where clean energy is available to everyone everywhere. It's a vision worth striving for. That's it for this deep dive into fusion energy, but the conversation doesn't end here. We encourage you to learn more, stay curious, and support the incredible work being done to make this dream a reality, because the future of energy is in our hands. Thanks for joining us, and we'll see you next time for another deep dive into the most fascinating topics shaping our world.